Hello. In today's lecture, we're going to be going through an introduction on differential equations, and then we're going to go through a few methods on solving first-order differential equations. Okay, but before we get to solving differential equations, what is a differential equation and how does it help us in physics? Okay, so we'll begin with the simplest case, first order. A first-order differential equation is an equation of the following form. Y prime, so the first derivative of y is equal to f of x and y. Okay, so that is as general as we can get. So this function f can depend on the independent variable x as well as y. Okay, and then this is equal to the first derivative. So we have an equation for how the function changes. We want to determine what the function actually is. So we have a description for how the function changes. And we would like to then determine what the function is. Okay, so this is very useful in physics because a lot of the times we model the changes in systems. So for example, we know at a certain time the particle is going to be at some point, and then at another time it's going to be at another point, and we know the velocity of the particle. So we know how the position changes with time. We can use the velocity to then find the position. Or in the case of Newton's second law, we know the acceleration because we know the force, and then from the acceleration we can get the velocity. From the velocity we can get the position. And we will look at all these examples. Okay, but before we get into that, I just want to go through all the different types of differential equations that we see in physics. Okay, so it's all throughout physics. I think you can even say the entirety of physics is looking at these different differential equations. So first we see them in classical mechanics. Okay, so that is all of the Newtonian mechanics with our F equals ma. Now, this doesn't look like a differential equation, but remember A is just the derivative of velocity, and velocity is the derivative of position. So we can write this as x double dot is equal to F over m. So in this case, we have ourselves a second order differential equation because we have two derivatives. So the order of the differential equation refers to how many times we are differentiating our function. Yeah, we also see differential equations in hydrodynamics. Yeah, so most famously, the Navier-Stokes equation. So that's rho, the time derivative of the velocity of the fluid, is equal to minus the gradient of the pressure plus the density times gravity plus mu, and then we have the second derivative of the velocity. So here we have a second order differential equation, okay, because it's the second derivative of the thing we're interested in. Okay, then in quantum mechanics, we saw this in the last chapter. Yeah, so in quantum mechanics, we have another differential equation, the Schrödinger equation. You can write that as minus h bar squared over 2m d2 psi by dx squared plus v psi equals e psi. And you see the first term here is the second derivative of our wave function. So it's a second order differential equation. Okay, other examples. Number 4. Maxwell's equations, so electromagnetism. So Maxwell's equations, those are a set of differential equations. And then just I'll write down one here. So we have the divergence of the electric field is the charge density over epsilon naught. This upside down triangle here, the nabla or del, that is a derivative. Yeah, so we've got a derivative of the electric field. So this is again a differential equation. Yeah, and lastly, even in very advanced physics, so as an example, Einstein's field equations for space-time. Einstein's field equations. Okay, so these don't look like a differential equation at all, but in fact, they are differential equations. Yep, sorry, minus. Yep, and then all of this is just equal to a constant times this thing we call the stress energy tensor. Don't worry about that. But this very complicated looking equation, again, it's just another differential equation that we need to solve. So we see that throughout physics, in many, many subfields of physics, we have differential equations. So they are very important to understand, very important for us to try and solve. Okay, so we will be solving these differential equations, not these ones here, but much simpler ones. We'll be solving them analytically, so pen and paper working out. We will also be solving them computationally. Yeah, and as we go through, we will see when we can solve it analytically. So under certain circumstances, we can solve it exactly with pen and paper. Other cases, we can't solve it exactly for whatever reasons we'll get into later. And instead, we're going to solve it computationally to get an approximate answer. Yeah, and we're going to be doing that in parallel for each of the problems. We're going to try to solve it analytically, we're going to solve it computationally, and compare our answers. Yeah, so that is the broad outline of what we're going to be doing in this chapter. Yeah, but first, we're going to be going through first-order differential equations. Okay, so first-order differential equations. We can just say DEs. Okay, so these are of the form y prime is equal to f of xy, as I showed in the previous page. Okay, so this is the simplest type of differential equation we're going to be looking at. And we're going to be looking at all the different methods of solving this. So given a particular function f, how can we then solve for y? Okay, so the first case and the simplest case is if this function f of xy only depends on x. Okay, so if that's the case, then we can use this first method. So f of x comma y is just some function of x. In other words, there's no y dependence in our right-hand side term. So in this case, we have y prime is equal to f of x. Okay, but that's very straightforward because we have the derivative on the left-hand side, that just depends on x. The right-hand side, that just depends on x. Now, we want to solve for y. So how do we get rid of the derivative? Well, we use our fundamental theorem of calculus. You covered that last year. We can just integrate both sides. So we can integrate y prime dx is the integral f of x dx. And don't forget our constant c. So we'll see here that for first order differential equations, we integrate once in this case, okay, to undo that the derivative, and we get a constant c. When we look at second order differential equations, we're going to be doing effectively two integrations, and so we're going to have two constants. Yeah, and we'll talk more about what those constants mean later on. Okay, so if we integrate the derivative, we just get the function back. So we have y is equal to the integral f of x dx plus c. Okay, so that is our general solution in this case. And we call this method direct integration because we are directly integrating. Okay, so this is called direct integration. Okay, so that is the simplest method of solving the differential equation. Okay, number 2, something a bit more difficult, is called separation of variables. So in that case, our f of xy is in fact separable. So what do we mean by separable? It means that this combined x and y function here can be written as the product g of x times h of y. In other words, we can separate all of the x dependence into g and all of the y dependence into h, and then the resulting g times h is our f. So sometimes we have this particular case. Okay, so in this case, we have the following differential equation. Y prime is equal to f of xy, but this is equal to g of x times h of y. Okay, so how do we then solve it if we know this is the case? Well, this y prime we can write as dy by dx is equal to g of x times h of y. Now, the dy by dx, it's not a fraction, but we're going to treat it as a fraction. So the dy is at the top, the dx is at the bottom. We can, in a sense, multiply both sides by dx, and we end up with dy is equal to g of x h of y dx. But now the right-hand side is a mix of x and y. So let's take the h of y to the other side. So we have dy over h of y is equal to g of x dx. Now we see that the left-hand side has only one variable y. The right-hand side has one variable x. We can then integrate. So integrating both sides, that gives us our function of y on the left-hand side, and then just a function on a function of x on the right-hand side. Remember to add your constant c. Now, since the left-hand side is a function of y, we need to invert that to then solve for y. So this side will be a function of y. We need to invert this if possible. Okay, so sometimes functions are not invertible, so we can't do that. So if it's invertible, to solve for y. Okay, so sometimes it's not invertible and we can't solve for y directly, but that's fine as well. We can still make use of the solution. Okay, and we will see that in the examples coming up. Okay, so this is separation of variables. It's the one of the methods we can use to solve the differential equations, but remember it has to be of this form here. Okay, if you can't separate it out like this, then we can't use this method. Okay, so that's number 2. Number 3, we have the method called integrating factor. Okay, so this method here, the method where we use an integrating factor, is when we have differential equations of the following form. So dy by dx plus p of x times y is equal to q of x. Okay, so given a differential equation of this form, we can simplify this with the use of what's called an integrating factor. So we won't go through the whole derivation now. We're going to do that in the next lecture. But we have this thing called mu, which we call the integrating factor, is e to the integral p of x dx. Okay. This looks very odd, but we will see where this comes from later. Using this, we can write the left-hand side as y times mu prime is equal to mu times q, like that. So now the left-hand side just has a derivative, and the right-hand side is just a function of x. So we can just integrate both sides. So integrate, dx. So this gives us y is equal to 1 over mu if we take that across, the integral of mu times q of x dx. Yeah, so that's going to be our general solution there. Yeah, but remember that when we integrate this bit here, remember we have our plus c. Okay, so that plus c is included before we take the mu over to the other side. So please don't forget your integrating constants. Okay, so this is just the general idea of what we're going to be doing. The actual derivation of how we get this mu and how we solve problems, we're going to be looking at that in the next lecture. Okay, and number 4, exact and inexact differential equations. Okay, so this is the last one that we're going to be going through for this chapter. So this is if we have the following case: dy by dx times p of xy plus q of xy is equal to 0. Okay, so that's one form of writing it out. Now, again, we can treat this dy by dx as a fraction, even though it's not, but it's helpful. So we can multiply through by dx, and we end up with p of xy dy plus q of xy dx is equal to 0. Yeah. So this is the form that we're going to be using. Now, from this, we have 2 different cases. So from here, we can do a check, and then this will result in 2 cases. So the first one is if we take the x derivative of the first part, p, so dp by dx, if this is equal to the y derivative of the second part, so dq dy, if that's the case, we call it exact. On the other hand, if it's not the case, so dp by dx is not equal to dq by dy, we call this inexact. Yeah. Now, if it is inexact, we can make it exact by using an integrating factor. Similar to what we did above here with this integrating factor. Okay, so we can make this exact. Okay, and again, we'll see how to do that later. So we can make this exact by using an integrating factor. Okay, similar to what we had before. Yeah, and then the general idea of what we want to do is, since this is exact, in either case, if it's exact, we can just continue. If it's inexact, we can make it exact. But given this differential equation, p of xy dx plus q of xy, dy, let's go back, p of xy dy plus q of xy dx is equal to 0. We can write this as the differential of another type of function. Sorry, not another type, just another function. Let's call it f. So let's say we have an f of xy such that the differential of f, there we will get to that as well. This remember how we calculate this. This is df by dx plus df by dy dy. Okay, so that's just taking the differential. If this is equal to p of xy dx plus q of xy dy. Okay, so we match up the differential there, the derivative. So df by dx is p, df by dy is q. If we can do that, then we've got ourselves the solution, because this is equal to 0 from above, which means that df is equal to 0, which means f was a constant. Let's just call that c. So if we can find this function f such that the derivative of f with respect to x, sorry, I mixed that up again. That's dy, that's dx, sorry. So it doesn't matter which order you have the p's and q's. So you can call the first one q and the second one p. Just make sure you match up the derivatives correctly. But we'll look at that later. So that needs to match and that needs to match. If we can find such a function f, then that gives us our solution. So this f of xy, if we can then solve for y, we have our solution. Okay, so that is the final case that we're going to be looking at, the so-called exact and inexact differential equations. Okay, so solving it like this is fairly easy. We're just finding this f, which we call the potential function. Okay, so that sounds like a very odd name, but we will see that this is very much related to the idea of an energy potential. So, you know, if you have two charged particles, there's an electric potential between them. Or if you have a particle in a gravitational field, you have a gravitational potential and so on. That idea of working with energy potential given a force field, that's very much related to this. Okay, so that's why we call it a potential function. Okay, and if that's not possible to do that, then we can find this integrating factor and then solve. Okay, so that is exact and inexact. Yeah, we'll go through the derivations of each of these methods and plenty of examples. Okay, so this lecture is just to introduce the different methods and just to show you what we're going to be going through. Okay, so this is first order differential equations. That's what we're covering this week. Next week, we'll be looking at second order differential equations. And then after that, we will go on to solving classical mechanic problems computationally. Okay, so that's the next chapter, where we will be using our knowledge of differential equations. Okay, so that's the plan for this week and next week. That's the plan for this week and next week. If you have any questions, please let me know. If you are struggling with that assignment or the tutorials that have been posted, again, please let me know and I can help you out. Okay, so please don't struggle on your own. I'm here to help. You can email me, visit me in my office, or we can make up some plan. But please, if you need help, just let me know. Okay, and then I'll see you in the in-person lectures for this week.